Welcome to this second lecture. So today we'll talk about the structure of real graphs. The basic question we'll address is the following. Are real graphs purely random? So here you have two examples. On the left you have the Karate Club, which is a real graph, and on the right you have a similar graph, the same number of nodes, the same average degree, but this one is purely random. And as you can see, there are clear differences, like if you look at the degree distribution represented by the respective sizes of the nodes, they are clearly different. Much more variables on the left, with the presence of nodes of high degrees, so-called hubs. There are other differences you may notice. One is on the distances. It turned out that distances between pairs of nodes are smaller on the left graph, which is not easy to see here, but we'll check that. And this is called the small world phenomena. And the last one is the presence of triangles. There are much more triangles in a real graph than in a purely random graph. Okay, so this is the outline of the course. We'll first focus on the degree distribution and talk about the power law, then on the distances, and this is related to the small world phenomenon, and finally on the presence of triangles and the clustering coefficient. So regarding the power law, it turned out that in most graphs, the degree distribution is highly variable, and a good model in general is a power law, let's say a Pareto distribution, which is the following: the probability that the degree D exceeds K is well modeled by something like that, where Km is the minimum degree and alpha is a parameter which is positive and which is typically between, let's say, 1 and 3. So what is interesting is that, for instance, if you look at the log of this probability, you get alpha log of Km minus alpha log of K. And on the left you have a constant, and so you have basically a linear behavior in log K. So if you plot this probability in log scale, starting from 1, 10 minus 1, 10 minus 2, the same here, degree 1, degree 100, and so on, you may observe something like that. This is a model, the Pareto model, and with a slope here which is typically between -3 and -1. In practice, you will observe not exactly a line, but something that is quite similar with a linear behavior. And this is, for instance, what you observe in a real graph, so Wikipedia Vitals, the vital pages of Wikipedia. Here, this is a directed graph, so we'll focus on the in-degree distribution. And as you can see, you have something that looks linear beyond, let's say, 50, a degree of 50. Okay, if you look here beyond 50, you have something that looks linear. Now the question is, it is really different from what you would observe in a purely random graph. So a good model, the reference model for random graph, is the Erdos-Streny model, where you take n nodes and you have an edge between two nodes with probability which is p, so this is a Bernoulli distribution. Okay, so you do that for all pairs of nodes. Okay, there may be an edge or node, and it's purely random. And now if you observe the degree distribution, so the degree has a binomial distribution with parameter n minus 1, all the other nodes, and p. And so for a large graph, let's say n is much higher than 1, and np tending to some constant lambda, so p tending to 0. This is approximately equal to Poisson distribution with parameter lambda. Okay, and the distribution is which you can plot here. So in orange you have a similar, so the Erdős-Rényi model corresponding to the Wikipedia Vitals parameter, the same number of nodes and the same average degree. And as you can see, the behavior is completely different. Okay, well, you may say that it's linear, but actually the slope would be minus infinity or something like that. And so actually the power law is not a good model for that. It's a Poisson distribution, and the tail distribution has nothing to do with the power law. Now the question is, why is this important? So first, let's try to sample edges at random in a random graph. So as we've seen in our first lecture, the degree distribution would be the bias distribution. So what is the bias distribution for a Poisson distribution? We've seen that, so we assume that the number of nodes is large, and so the degree distribution is typically a Poisson in an Erdős-Rényi graph. So the bias distribution would be proportional to k, the original Poisson distribution, and this one is explicit. You can check that this is actually equal to the probability that d is equal to k, given that the degree is higher than 1. You cannot have a degree equal to 0 through edge sampling. And so you can do the computation. If you compute the expected degree, for instance, it is equal to the expected degree through node sampling plus 1, which means that the difference between node sampling and edge sampling is quite negligible. If you have an expected degree of, let's say, 100, you wouldn't notice any difference. Now, what happens with the power law graph? Well, here the story is very different. So if you compute the expected degree through edge sampling, we've seen that this is related to the second moment of the empirical degree distribution, and this can be written as follows. This is the expected degree through node sampling plus times 1 plus the coefficient of variation, okay, square. And the coefficient of variation is the ratio of the standard deviation to the mean. And for a power law, so this is general, actually this is true for any distribution, but now the explicit expression for a power law is 1 over alpha times alpha minus 2 for alpha larger than 2, and actually this is infinite if alpha is less than 2. Okay, and so here you can see that the impact of edge sampling, of the sampling strategy on the expected degree is huge. Okay, you have here a multiplicative factor that may be quite large. So how large is this in practice? Well, you have this plot by Barabasi, his book on network science, and in this plot you have on the y-axis the standard deviation, the x-axis the average degree. So here on the green dots correspond to a Poisson distribution. So let's say a random graph, and for a coefficient of variation equal to 1, you would get something like that. Okay, so this would be a coefficient of variation equal to 1. And as you can see, most real graph have a coefficient variation which can be higher or even much higher than 1, okay, which means that the impact on edge sampling is strong. And these graphs are called scale-free because actually the standard deviation may be very large, and in practice it means that the degree distribution is so variable that the average degree does not say much about the degree of an arbitrary node. An interesting question is now, where does this come from? Why do you find this power law almost everywhere in real graphs? And Barabasi and Albert proposed a model in 1999, which is a very simple model that explains this power law. It is based on this notion of preferential attachment. So you start from a clique of D nodes. So here D is equal to 3, you have a triangle. And then you add new nodes, one after the other, each of degree D, with preferential attachment, which means that you will attach them to the previous nodes in proportion to their degrees. Okay, so for the very first node, degree 3, you don't have choice, you will attach to the original 3 nodes. Now for the next one, all previous nodes have degree 3, and so you can choose one of these nodes at random. Now for the next node, as you can see, so again you will attach this node to the previous nodes by 3 edges, but now if you have a look, there are 3 nodes having degree 4 and 1 node having degree 3, and so it's more likely that you will be connected to the nodes of degree 4. It's not a rule, you may be attached to the other one, but it's more likely. And this simple phenomenon, the rich get richer, mean that you will at the end create rich nodes, which means hubs having a high number of connection to the rest of the ball. Okay, so you do this again for each node, and you get a graph with hubs, and you can prove actually that when n tends to infinity, you get a power law. Okay, so this is a very simple explanation of this phenomenon due to the dynamic nature of graphs, the way they are created in practice. So this is a simple example of a generation of a power law graph by the Albert Barabasi model with 100 nodes. So the blue nodes here are the initial 3, the initial triangle, and you can see that the degree distribution is highly variable.